The helicopter can do a lot of things that a conventional aircraft cannot do. It can hover and reverse and is extremely maneuverable. As they proved in Vietnam, helicopters have become an indispensable part of the modern battlefield. They can act as stable, heavy-fire gun platforms in support of ground troops or acting independently, rush troops into battle, or pluck a downed pilot from a jungle. One thing that a helicopter cannot do, that a conventional plane can, is achieve a high speed. There is a pretty well absolute limit to how fast they can go because of the differences in speed at various points on their rotors. The tip may be travelling at near supersonic speed, while the helicopter is doing only 200 miles an hour. Even compound helicopters, with winglets and forward-thrusting engines, suffer enormous drag penalties from the rotors and cannot be expected to easily approach the speeds attained by a modern fighter. But helicopters do what they do extremely well, and there are many applications, not only military, ideally suited to a helicopter. The biggest advantage they have can be put very simply: they can fly vertically. It is the justification for their existence. They can land on ordinary ships, in fields or forest clearings. They can take off from virtually anywhere, and if they can't land somewhere, they can hover just above it. If only they weren't so slow. Helicopters are only 50 years old, and yet they've developed so fast that their limits have not only been deduced, they've been reached. Modern combat aircraft have become increasingly addicted to concrete, miles of it, straight and flat, with acres of parking bays and hard stands, and so have their support aircraft. All of this is expensive and requires massive permanent bases to support the concrete. These bases are scattered around the globe, serving every potential belligerent in the various alliances and hostile camps. Any theory of conventional modern warfare worth its salt is based around a preliminary battle for air superiority, either on a local or theatre level. And the easiest way to do this is to destroy the infrastructure needed to support an aerial force. In effect, the airfields are huge, immovable targets. Some countries have made their highways with straight stretches that are strengthened to act as dispersal sites for their planes in emergency, foreseeing what would happen to their bases. The idea of a rocket-assisted takeoff works better if your plane is actually capable of flight and if your rocket is powerful and safe enough to use. A rocket-assisted takeoff gives two major benefits. First, it allows fuel savings in getting a specified load into the air, and second, it shortens the takeoff. These benefits have long been recognized, and powerful working systems of rocket and jet-assisted takeoff, RATO and JATO, have been highly developed at times, though they've not always been particularly safe to be around. One enthusiastic user of such systems was the Second World War German Luftwaffe. They plugged their highly efficient, though cantankerous and dangerous little rocket pods onto just about every plane they had at one time or another, with considerable success. Enormous quantities of fuel are normally consumed at takeoff, and to be able to lessen that demand can considerably increase a plane's range. The second benefit, that of a shortened runway, has become more important subsequently as planes have become less and less tolerant of rough ground conditions. It should be noted that German airfields became bomb crater collections on an almost permanent basis through much of the final phases of the war, and shortened takeoff would have certainly been a virtue. The chemicals involved in these rocket engines were highly active and required careful and methodical handling. The violence of the reactions to occur in firing the rocket could all too easily be set off by accident, and the results of such accidents could be devastating. The protective clothing was worn with alacrity in recognition of the danger. Flying boats gained considerably from the use of rocket-assisted takeoff. Normally, a flying boat required a long run to unstick itself from the water, and the fuel tax of this was enormous. Then again, for a flying boat, it's impossible to actually damage the runway. The United States was another user of Rato, and extensive testing of various units was undertaken. Here, a Martin B-26 gets a rocket shove to reduce its runway use enormously. The interest in Rato grew considerably with the arrival of the jet engine. Jets had their special needs, and high on the list is the long concrete runway. Jet engines are susceptible to damage from ground debris and also tend to have high takeoff and landing speeds. Their advantages come into play in the air. On the ground, they demand mollycoddling. The world's air forces had to come to grips with the problem of the runway, despite their acute awareness of their vulnerability. Rocket and jet assistants still were of more benefit in fuel savings than they were in shortening takeoff length, and required their own additional backup, personnel and supplies, including some stores that were highly volatile. As systems, their inherent deficiencies and clumsiness made their overall use limited. Though a lot of effort went into the various attempts to make workable setups available, their widespread utilization remained impractical. The most extreme scheme to use assisted takeoff to do away with runways was the zero-length launch system. This can perhaps best be described as shooting aeroplanes off of the back of trucks. Tests of the idea were carried out with various aircraft, with surprising success, considering how odd the aim appears to be on the surface. The launch apparatus was developed by the Martin Company, with the obvious aim of increasing the dispersal of aircraft and lessening their attachment to established bases. The first launching was conducted on the 15th of December 1953, with an unserviceable, unmanned F-84 being shot off into the desert. The first piloted launch was made on the 5th of January 1954. Recorded acceleration loads were only 3.5 Gs, marginally above a standard aircraft carrier catapult launch. When the few seconds of rocket burn were over, the plane had been brought up to a speed of 175 miles per hour, well above the F-84's stall speed, and the pilots reported no difficulty in controlling the aircraft. Zero-length launch worked, but it didn't really answer the need for aircraft that could take off vertically in a practical way, and though it was refined and applied to several aircraft types, it was in the end abandoned. What was needed was the ability for fixed-wing aeroplanes to take off in the same way as rotary-wing aircraft, straight up. And there has been constant research and development of various ideas to achieve that. Perhaps one of the more immediate solutions to present itself was to use an aircraft's propellers as rotary wings on a horizontal plane to get into the air, and then to swivel them to a vertical attitude for level flight. The Bell XV3 tilt rotor, completed in 1955, worked from this theory, and indeed its propellers were very reminiscent of a helicopter's rotors. It was to fly for 15 years and provided a lot of valuable information. The Curtiss-Wright X-19 aircraft used propellers rather than rotors, although their shape was highly exaggerated, with very broad chord and extravagant twist. These were driven by two engines mounted side by side in the fuselage, through a complex series of gearboxes and shafts that could be run by one or both of the engines. Two planes were built, but only one flew. The program was cancelled before the second one could take to the air. The test series was short, disrupted by mechanical troubles, and rounded off with an in-flight failure on the test plane that saw it crash. In the period from its first tentative hover in November 1963 to the crash in August 1964, the plane left the ground only 50 times, for a total accumulated flying time of less than 4 hours. The X-19 had developed from an earlier Curtiss-Wright privately funded test aircraft, and the two demonstrated enough about the concept of tilt propellers to suggest that the system had its advantages, encouraging the company to further research and development, though to this date this has not led to any further aircraft. Doing away with the complex drive mechanisms, Bell's XV15 tilted its engines, which were, to allow this, mounted on the tips of its wings. They drove large propellers that were a compromise between the requirements of helicopter rotor and aircraft propeller. The XV15 made its first hovering flight on the 3rd of May 1977, and the two examples constructed have been highly successful, making hundreds of flights. The first actual transition from helicopter mode to level flight was made in July 1979, and the program has been so convincing that by 1983, the US Navy had ordered a development of the plane into production as the V-22 Osprey. With all the systems that require a plane to behave as a helicopter and then change over to level flight, there are two very difficult areas to sort out. The first difficulty is to give sufficient control to the pilot during the helicopter flight mode. And the second is to safely go through the actual transition to behaving like a normal aeroplane. After that, as they say, it's a piece of cake, until the time comes to reverse the process and land. The idea of tilting various bits of the airframe to provide both takeoff lift and then forward thrust has also been repeatedly applied to the entire wing, engines included. This allows a less artificial positioning of the engines than sticking them to the end of the wing, and can allow the wing control surfaces to be used to control the plane in hover. However, it means that the surface that is to provide in-flight lift has to be transitioned to level flight, and this presents a very difficult phase, where the propellers cease to act as rotary wings before the wing itself is actually working to keep the plane in the air. The Vertol Model 76, developed as a test craft for the Army and Navy, flew from 1957 to its retirement in 1965, and in that time made hundreds of successful flights. It was a very influential little plane, with much of the work done in sorting out its controls and giving it reasonable stability flowing on to inform later tilt-wing projects. Perhaps the most important of its successes was built for the Air Force by an LTV Hillier Ryan consortium. based on Hillier's earlier X-18 craft, which had exhibited some vices in its career, particularly in hover control. The new plane was to be a much larger and more ambitious project, and was built to a 1961 Department of Defense specification to meet the needs of the services for a VTOL transport. It was given the number XC142, signifying very clearly that the intention was for the plane to go into full production. Five of the planes were built, 4-engined, 58-foot long, and with a 67-foot wingspan. Their proportions suggest that they are small planes, but they are quite big. They had a gross weight vertical takeoff capability of 41,000 pounds, which made them quite a well-sized proposition for carrier resupply or battlefield aircraft. The propellers were not linked directly to the engines, but to a common cross shaft. This guarded against asymmetric behavior should one of the engines quit with the plane in hover, which would otherwise have led to certain disaster. There was a lot that worked about the XC142, but there was enough that didn't work to keep it from mass production. After the experience on the project, there was a lot of talk about getting back to the drawing board. Among its vices were transmission failures in the complex cross-linking, and that system's intolerance of wing flex. What may be small problems in level flight become major if they occur during hover. And in the period of testing of the XC142s, 4 of the 5 were badly damaged in accidents while in hover position. The overwhelming problem with them was, however, that they vibrated badly and were almost insanely noisy. Up against the much bigger Hercules, carrying 3 times the load, twice the distance, relatively quietly, and with short takeoff and landing to boot, the XC142 tiltwing, while still capable of being further developed, was abandoned. Aircraft with tilting ducts were another variation on the theme of swiveling parts of the aircraft, somewhat similar to the tilt props. The ducts had several additional virtues, in that they augmented the propeller thrust and also worked as additional wing surface in level flight. Vanes inside the duct could be used to give better control at delicate points during transition, and propeller turbulence was kept away from the wing. The Doak Model 16, completed in 1957, was among the most successful of early vertical takeoff aircraft, and provided NASA, who conducted tests on it in conjunction with the Army, with much information. In particular, studies of the plane's power needs in hover and in transitional flight made increasingly clear the enormity of the task ahead in the pursuit of truly practical vertical takeoff aeroplanes. The ducted fan system actually has a lot to recommend it. The Bell Corporation's 2 X-22As effectively proved the idea as workable and very effective in a long career. The X-22 first flew in March 1966. In August of that year, one was damaged beyond repair, but the other was to fly on till 1984 and was retired, still flyable, to museum life. The X-22's contribution to the science of flight was not limited to the ducted system, but it did show that the system works. And though there have to date not been any production aircraft using the configuration, the work of the X-22 still serves as a reminder of its potential. Another point about fans that had been established was that they considerably increased the effectiveness of jet engines in producing hover thrust, and this was the basis of the turbojet-powered Ryan XV5A. The engine's thrust could be used either normally to propel the plane in level flight, or diverted to the fans for hover mode. The 2 main lifting fans were embedded in the wing, with another stabilizing fan in the nose. Once airborne, the fan's airflow was deflected by vanes to start the plane forward, and then the engine's thrust was diverted to the jet pipes and the fan covers in the wing were closed, theoretically leaving a handy little fighter plane. The disadvantages included the domination of the available space in the plane by all that ducting, fans and engine. However, there was a lot of promise to the use of fans with jets, and Ryan published proposals for a variety of applications, including high-speed interceptors, heavy transports and passenger airliners. All of these various avenues to vertical flight were being tested at the same time. The end of the Second World War had set off a period of reflection on the lessons for future warfare, and there had been several important factors indicating that vertical takeoff aircraft were of the highest priority of need. The US Navy, not as beset by concrete as the Air Force, had its own problems, one of which was the experience of locking up large numbers of expensive warships with escorting creeping convoys of merchant shipping. To release some of these warships for other duties, it would help if the merchantmen could carry more of their own defences. And from this came one of the earliest VTOL design competitions, with contracts going to two manufacturers, Convair and Lockheed, to build prototypes of midget VTOL fighters to operate from cargo ships. They were both to operate as tail-sitters. The Lockheed plane was given the designation XFV1. Its configuration sprang from the active mind of Kelly Johnson, Lockheed's design wizard. The plane, called the Salmon, after a period of experimentation and development, refining the elements of its shape, came out looking superficially quite similar overall to a conventional small propeller-driven aircraft. The biggest variation from the norm in its shape was the 45-degree angling of the set of 4 tail fins that graced its rear. Construction of the Salmon proceeded fairly smoothly, and there was to be only 4 years between the order and the first flight of what must be conceded to be a very radical proposal. In that time, an enormous number of problems had to be confronted and overcome. From the position of the pilot to the use of casters on the fin tips as undercarriage, there were many aspects of the plane that were unique. While construction proceeded on some parts of the main assembly, development work continued alongside, refining other components and overcoming many problems that would ordinarily never concern an aircraft designer. The position of the pilot was one area that caused a lot of problems, and a satisfactory arrangement was never really sorted out. Other areas of the plane's special requirements, like maintaining fuel flow, were, however, resolved. Also overcome was the problem of undercarriage capable of settling the plane onto its tail in landing. Given the impossibility of setting what direction the tail would be moving in hover at the instant of touchdown, or of guaranteeing truly vertical descent or a level landing platform on a boat at sea, the problem was complex. The solution looks deceptively simple, suggesting the wheels of a shopping trolley. A further complication around the pilot's position was the absolute necessity to be able to eject safely. There was obviously no way a normal ejection seat would do anything but shoot the pilot into the ground if used in a hover, and a special seat was designed to shoot the pilot up or forward, depending upon the plane's attitude. Because it didn't shoot him straight up, but at an angle, it also needed to throw him further to attain a useful height for a parachute to open. The system was, understandably, extensively honed over a series of tests. The XFV-1 was fitted with temporary fixed conventional landing gear for its first test flight series, it being wisely acknowledged as necessary that the plane proved that it actually flew controllably in normal operation before proceeding with the more adventurous business of standing it on its tail. Even while undergoing its taxi tests, it showed a willingness to get airborne, and its first flight passed without problem. In level flight, the little plane proved to have no daunting vices, and the series proceeded to high-altitude test transitions. Here, problems were encountered, including one that was very serious and was not to be overcome. In transition from level to vertical flight, the plane's momentum saw it gain several hundred feet before it stabilized in hover. The pilot, with his back to the ground, was therefore left in a skittish and difficult to maneuver aircraft, trying to lower himself with little to no idea of what was below him or how far away it was. Even screwing his neck round, he couldn't see much below him. This was obviously going to make landings significantly more difficult than was desirable, especially if one keeps in mind the deck of a freighter or a destroyer in mid-Atlantic. Despite the worrying experience of the pilots in hover, the tests went on to their next phase, to actually take off in the plane. Here, another insurmountable problem arose with the plane's available power. There simply wasn't enough of it. In addition, there was inadequate control available to the pilot in hover. The combination of these factors, which made attempts at takeoff nearly impossible, allied to the experience of the pilots in preparing for any vertical landings, experienced in the air, and a very unnerving prospect to look forward to, was enough to seal the fate of the project. It was written off as a learning experience, and the plane was retired. If one were desperate for a failure to attribute to Kelly Johnson to offset his stream of resounding triumphs, then the XFV-1 might be it. However, as a test plane, it answered a lot of questions, and it posed a set of new and very interesting problems for those working on vertical takeoff aircraft. The other plane ordered in the 1950 decision, Convair's XF-Y1 Pogo, proceeded in parallel and in competition with the Lockheed plane and did not have that experience to draw on. However, it was a very different design, being a delta-winged plane with dorsal and ventral fins matching the wings. The multitude of control surfaces still struggled to get enough grip on the propeller's slipstream to give much stability to hovering flight. But in many other aspects, the plane worked quite well. The Delta gave it more strength for less weight, and also gave it much better performance at low speeds and high angles of attack, obviously important in the transitions at takeoff and before landing. Unlike the Lockheed plane, there was no way to configure the Pogo for level takeoff, and so its first flight also included its first vertical takeoff and landing. The experience the Lockheed pilots had already had was repeated in the Convair plane. Though it was far more capable of carrying out the transitions and actually taking off and landing, there was still no way for the pilot to see what was happening once he was in hover, staring at the sky. The coaching of ground crew by radio was of some assistance. But in all the tests of the tail-sitters, the situation of the pilot in landing was unsatisfactory. The powerful Allison engine would drag the plane up before settling into the hover, and the blind descent was a nightmare. Another notable vertical attitude plane was the Bell X-13. The preliminary work on the problems of the feasibility of reaction controls for jet aircraft had begun in 1947, backed by the US Navy, with the same objective that had created the Pogo and Salmon, self-defending convoys. When the Navy ran out of funds, the Air Force's attention was already rising in relation to its own needs, and the X-13 vertijets were to fill an Air Force order. The secret of the X-13 was that it hung on a hook and was designed to operate from a trailer. After a careful series of gradual steps ironing the problems out as they went, the team working on the project achieved what, on the face of it, seems an improbable aim: a portable plane complete with aerodrome. The system worked quite well, but after the initial fanfare of astonished applause when the plane first strutted its stuff, it seems to have immediately faded into an impenetrable obscurity. The two X-13s were among the most successful early jet VTOL aircraft, and the success and efficiency of their unlikely-sounding mission was perhaps as advanced as anything in the vertical field before the Harrier. They proved that vertical flight on jet thrust alone was both technically feasible and practical, and left little to question about the flexibility and usefulness of such an arrangement. But there would have been a way left to go to get it operational. The pilots still could not see, and there were loading limitations. Even without the weight of the retractable undercarriage, the thrust of the available engines left little reserve of power. The X-13 idea could have been refined, but it's highly unlikely now that it ever will be. Using jets to obtain sufficient thrust to go straight up required a lot more power from the engine than was readily available until quite recently. And the seemingly obvious solution to this was to have two sets of motors, with one set only involved in getting into the air. Hence the Rolls-Royce flying bedstead, which was involved in trying to sort out the tricky business of developing controls for a plane that's rising on a pillar of jet thrust. The system developed on such vehicles operates very much in the same way as the lunar lander. The principle of control is reaction jets. It was still true that the accident that happened in Hover was generally going to leave no time for recovery, but the work done with aircraft like these broke down a lot of the barriers standing in the way of vertical flight and made possible the use of far more conventional aeroplane shapes in VTOL roles, though of course they themselves don't look like conventional aircraft at all. Where the Bell X-13 had quite practically hung itself up on a hook after a flight, there's been a lot of work on various systems for shortening the required landing length of aircraft, including another apparently fairly outrageous suggestion: to grab them with an arrestor hook and then slam them on their bellies on a rubber runway. Yet this too has been taken to the point where it actually works and has been extensively tested. It was developed by the British, but the Martin Company showed a lot of interest in it as a companion system for their zero-length launch trucks, and the British showed the system off to several impressed American delegations. Despite the potential to miss the hook and sail back over the ship's side on occasion, the system worked after a fashion and obviously cannot have been as silly as it sounds. Of course, crash barriers and arrestor wires have long been refined aboard carriers, and many planes have been fitted at one time or another to operate with these mechanical interventions. Apart from extreme examples like the rubber runway concept, the planes have clung to the weight penalty of their wheels, and most of the time such landings are routine and go through without incident, though it does remain hazardous. If nothing else, the rubber runway serves to remind us of the lengths to which experimentation was pushed in trying to bring the demands of aircraft for takeoff and landing distance to heel. Vertical takeoff experimentation saw another variation in the Bell Model 65 with its swivelling jet engine. It had a relatively short career, and though it flew with the engine in both positions, it never did so on the same flight. No full transitions were made with the little plane. However, it settled several important basic issues and gave Bell the information it needed to proceed with its next, more ambitious design proposal. The Model 65 used engines off a missile, and when they burnt out after 4.5 hours use, that was the end of the project. One thing the Model 65 does well is show off its control jets. The nozzles can clearly be seen in the end of the wing, and the ducting along the side to take the compressed air to the rear cluster of nozzles is also evident. By constant and sometimes painful trial and error, the controls needed to hold a plane in relative obedience while hovering have been sorted out. The normal method of control with jet-engined VTOL planes is the use of air pumped to the plane's extremities, being vented as needed to hold position. In early wind tunnel tests with large working models of the system, 4 pilots sat at controls operating different bits. It was extremely complicated. Now, though not less complicated, it's a lot more automated. The Bell company has been absorbed in vertical flight research from the early 40s and has constructed an impressive range of prototypes exploring different approaches to the problems of getting a plane into the air without a huge runway. In 1956, they won a contract with the US Air Force to build a new plane, given the name X-14, to test their work on the concept of thrust vectoring and to serve as a test bed to sort out how to give pilots sensible controls for hovering flight, an area that was then still resolutely proving difficult. The X-14 was to be one of the most important aircraft in the long saga of vertical flight experimentation. In 1954 and 55, Bell had gone to the Air Force with a proposal for a VTOL lightweight day fighter and had managed to get the Air Force very interested in the proposal. As a step in exploring the technology that would be needed for such a plane, the Air Force had authorized the company to build a technology testbed aircraft. Bell's primary concern was to test the use of vectored thrust, which seemed to offer the simplest solution to the use of jet engines, allowing a plane that sat in a horizontal attitude. The test plane was built as fast as possible and as cheaply as possible, which coincidentally led to it being as small as possible. It incorporated existing engines and scavenged its parts from all sorts of aircraft spares. It had no canopy and no ejector seat. It was the minimum needed to do the job. The scheme of vectored thrust is to blow the hot engine exhaust through movable grills that aim them either at the ground or to the rear of the plane. On the face of it, a very simple approach. However, as is usual in these things, there are many complications. For example, if you point a powerful jet engine at something at close range, it is likely to do considerable damage. It will dig a pit in your lawn, or it will make your concrete bubble and smoke alarmingly. As a result, one of the things that the engineers working on the X-14 project had to turn their attention to was the constitution of concrete and how to build a heat and blast-resistant surface for the X-14 to test on. Here, if you'll pardon the expression, is the concrete embodiment of the X-plane series. Aviation's history is the chronology of a cascade of ideas, forming in the minds of individuals and being honed, expanded, or debunked. The generations of knowledge have succeeded one another at a bewildering speed, drawing constantly on what is proven to imagine what might be provable. It's been only when a hypothesis is put to the test that its full meaning has been discovered, both in the significance, success, and implication of the idea, and also in the snags, complications, side effects, hazards, and failure. On 2 levels, the X series enriched aviation by turning theory into hardware and then turning that hardware into practical machines. There are so many famous firsts associated with the X series: breaking the sound barriers, testing new materials, swing wings, high-altitude flight. The X-14 itself was the first vectored thrust aircraft. In addition, there have been thousands of less famous firsts associated with technical advances, control systems, and avionics. Much of what is known about flight today, and affects the planes of today and will affect those of tomorrow, rests on the results obtained by planes in the X series. It even seems likely that the X-14 may have been the first aircraft to have a pink circle for landing and takeoff. The X-14's flight test program started on the 17th of February 1957, and it completed the evaluation series for Bell in 1959. The Air Force then taking the plane over for an extended series of further general VTOL testing and pilot familiarization. Extended seems an inadequate word, actually, as the plane was to continue to be used by the Air Force and NASA until the 29th of May 1981. It was that day damaged in an accident and was written off as no longer airworthy. Today, fittingly for such a productive and successful little pioneer, it's preserved in a museum. Work on various schemes continued all over the world. In Germany, the Dornier 31 was a combination of lift jet and vectored thrust configurations. The Lockheed Company invested a lot of its energy in augmented jet lift, in yet another method of heaving a plane straight up. Here, the theory stated that introducing jet thrust into a chamber of air would create additional lift from the engine's power by the rush of air into the chamber. And this was undoubtedly true, as it had been repeatedly shown to occur in test installations. However, in working the system into an aeroplane, the weight penalties of the installation went a long way to cancelling out the augmented thrust of the power plant, and Lockheed's Hummingbird was not a raging success, being later rebuilt with dedicated lift engines to test a completely different configuration. The use of lift-only jets by Lockheed and Dornier followed what seemed to be the emerging dominant pattern, using a number of small jets which only worked when the plane was in hover. The main engines were much larger power plants which operated in all phases of flight. The weight penalties of this are obvious, but they would be partially compensated for. A plane that had only its main power plant to obtain lift would need an extravagantly big engine, which would, in normal flight, never be called upon to deliver much of its available power. Of course, what happened to change the status quo was a breakthrough engine, developed by the Bristol Company in England, the Pegasus. Around this engine, the Hawker Company were able to develop their P1127, forerunner of the Kestrel and then the Harrier. The 1127 was a major step forward, an emphatic proof of the thrust vectoring approach, and drew extensively on the data obtained in the X-14 program. It was designed around the new engine, but for once, this did not place too unreasonable a set of demands upon the plane's shape or capability. The creation of a new engine is an expensive business, and to create a new engine for one application places a huge research and development load onto only one customer. And in the case of the P1127 and its basic development into the Kestrel, a lot of cost went into producing only a handful of aeroplanes. When the Kestrel project was completed, a lot of time and effort was put into design of a supersonic version, the P1154. And this almost caused the abandonment of the whole area of research by the company, due to the huge bills involved and the lack of UK government support. Eventually, the plane that did emerge from Hawker's was a subsonic fighter, and initially there was little to no enthusiasm from the fighter pilots, who preferred to be at the controls of something that went considerably faster, preferably with as much glamour as possible. Today, the Harrier has come a long way, and the new AV8B model incorporates a large number of advances and improvements. Though still subsonic, it now has doubled load capacity and range. The Harrier's successful use in combat and the successful development of tactics for its pilots have combined to underline that it is one of today's most potent and dangerous fighting machines, and it has been adopted for various uses. The McDonnell Douglas Company has been involved in the project, together with British Aerospace, and the two companies have cooperatively developed the Harrier's capability and refined its airframe to ensure that it remains the most capable vertical takeoff plane in the world, at least for the moment. Who knows what'll be next, or what method it'll use. Next in Strange Planes, why do planes look like they do? And how did they get that way? Don't miss Strange Shapes,